Previous lecture, we discussed about velocity Verlet algorithm, how we can use this algorithm to calculate the position and the velocity of particles in the system at any instant of time. So, as we saw that we can easily calculate the position at any time t plus delta t using this formula, but to calculate the velocity at t plus delta t, it's very important to calculate the force at time t and force at time t plus delta t. So we have a formula here as force equal to negative gradient of interaction potential. So it's very important to know what this interaction potential is before we calculate the force using this interaction potential. So I will be using Lennard-Jones potential to calculate forces on the particles in the system. So what is Lennard-Jones potential and how to use it in our system to calculate the forces? It's very important to discuss what this potential is. So this is the expression for Lennard-Jones potential, and here we have interaction potential or LJ potential. It is represented by V as a function of R. So it is equal to 4 epsilon sigma by R whole raised to power 12 minus sigma by R whole raised to power 6. So epsilon here is the unit of energy, and sigma is here is the unit of length, and r is here distance between centers of two molecules. So let us consider that I have a system that is consist of n number of particles that are interacting with each other. So if I pick up any two particles, then the distance between their centers is going to be r. So, and let us consider that if the radius of that particle is sigma by 2, or the interacting particles are sigma by 2, then their diameter is going to be sigma. And also, if I bring them closer to each other, so when they come in contact with each other, the distance between their centers become sigma. So here r is equal to sigma. So now let us try to understand this curve here. So here on the y-axis we have interaction potential, on the x-axis we have distance between the centers of two molecules. So the distance here up to is sigma, here r is equal to sigma. So what does this mean? So if I bring my molecules more and more closer to each other, so they overlap with each other. So when they overlap with each other, when they overlap with each other, so the value of r here is less than sigma. So when the value of r is less than sigma, so you can see the sudden rise in the curve. Okay, and this is representing the repulsive potential here, sigma by r raised to power 12. So what happen when you bring them more and more closer, the distance less than sigma, what happen, the molecules start repelling each other. And what happen if you keep on increasing the distance between them as the r goes on increasing? So there are going to be weakly attractive forces that are going to exist between these molecules, and you can see here it is represented by sigma by r whole raised to power 6. And epsilon is the unit of energy and sigma is the unit of length. So whatever distance we are going to take in case of in LJ potential, it is always written in terms of sigma, and whatever energy we are calculating in our system, it is always be in the units of or in terms of epsilon. And you can see here that this is the point in the curve where it has its minimum value. So as you can see here that the slope of this curve is also equal to 0. To find the minimum value of potential or minimum value of energy at this point, we have to put the slope of slope of this curve equal to 0 at this point, as we can see here. So to find the minimum of this potential, we have to put dB upon dr equal to 0. So we have to find the derivative of interaction potential, and it's very simple derivative, it's not very complex. So when you will find its derivative with respect to r, what you are going to get is r equal to 2 raised to power 1 by 6 into sigma. So this is the distance between the two particles when they have minimum interaction potential, or they are going to have minimum amount of energy. So this is the distance here, 2 raised to power 1 by 6 into sigma. Now one of the most important thing is the uh, RC, that is the cutoff distance that we have to uh, provide during our simulation. So let us consider that this is our system that we are going to study, or our simulation box. These are the number of atoms in our simulation box. So to better understand the cutoff distance, let us consider that the cutoff distance is 2.5 nanometer. Let us consider that. So now if I take this particle for the understanding of cutoff distance, let us consider that all the particles in the neighborhood of this particle, let us say that this one, this one, this one, this one, and this one. So all these five particles, the distance of this particle from all these five particles is less than 2.5 nanometer, or is less than our cutoff distance. So there is always going to be have some interaction between these particles, and due to this interaction, the force acting on this particular molecule is always dependent upon its interaction between with these particles in its neighborhood, where the distance is less than the cutoff distance. What if I have a particle here? Let us consider this particle, and if the distance between them is greater than the cutoff distance, is greater than 2.5 nanometers, so there is going to be no interaction between these molecules. So this is the expression for Lennard Jones potential, that for if the distance between two particles is less than the cutoff distance, so there always going to be some interaction between the particles in the system. But when the distance is greater than the cutoff radius, there is going to be no interaction between the particles in the system, and the value of interaction potential is going to be 0.